So let's recall last time we finished the proof of this Ramsey K4 versus complete graph, the construction, recall? We did this random block construction to prove that K4 versus KT is up to a Holy log factor, roughly t to the power 3. And I have a couple of remarks to finish these results. The first remark is that some open problems, some of which are quite important open problems. So remarks. First one is about pseudo-random graphs, optimal pseudo-random graphs. So pseudo-random graph means the graphs which behaves like random graph. And one of the criterion to define such pseudo-randomness is to look at the spectrum gap when, let's say, the graph is regular and the non-trivial eigenvalues, they are much smaller compared to the first eigenvalue, which is the degree of the graph, the regularity. So here, let's along, for example, construct a triangle free. It's called ND lambda graph, which is an M vertex, the regular, and all the other let's say we order the eigenvalues in decreasing order, lambda 1 to lambda n. So lambda 1, this is lambda 1. But the remaining, they can be bounded in absolute value by lambda. And ideally, we want to have lambda much smaller than d to be pseudo-random, right? So we would like lambda to be much smaller than d to be pseudo-random. So pseudo-randomness is a huge topic. We don't have time to talk too much about it. Let's just say that it has many connections and applications, including having an alternative construction here for the using such pseudo-random graphs. But it goes along the similar line as this random block construction. So what our long proof is there exists a dense triangle free. So perhaps I should say there exists triangle free such ND lambda graph where how dense it is, the density could be as dense as n to the 2/3, and lambda is almost optimal in terms of spectrum gap. So we know that lambda cannot be smaller than some constant times square root d. So here we say it's at most some constant times square root d, which is optimal up to the constants. So this is known along results. What's open is the next case. What about K4 free, or in general, KS free? So find, does there exist K4 free and the lambda graph where B is n to the 4/5 and lambda is almost optimal, small. Okay. So if this is true, the density will be optimal. but the graph HQ that we use, or HQ star, their spectrum, the lambda is not strong enough to fit in here. That's the first remark to work here. So the second remark is about a problem called Zarankiewicz problem in extremal graph theory. Zarankiewicz problem. So this is the problem. We have a parameter z n m. You have two parts, m vertices on one part, m vertices on the other part. And then we are forbidding this K4 1. This is one subdivision of K4. One subdivision of K4 just means you have these four core vertices. How do I draw it? Right? These are the four core vertices. Originally, we have these edges. Now we subdivide every vertex by one vertex, one subdivided once. So you have six subdivided vertices, six new vertices. And four original ones, right? Now what we're forbidding is this number is the maximum number of edges in an m by m vertex bipartite graph G. So here n by m in G. What we're forbidding is we don't want this one subdivision of K4 with four vertices in the part of n. So you don't want four vertices here and six vertices here, forming a subdivision of K4. Okay. Let's say it's like this. I will not draw all the edges just to illustrate. With no K4 1, which does not contain K4 1 with four original vertices on the m vertex side and six new vertices on the m vertex side. So it looks a little bit strange why we cared about one subdivision of K4. Actually, from our graph, the HQ star, and when we take the so if we consider the point line incidence graph, of the line of all of these unitals and seconds, I believe, right? Then it does not have this K4. No such K4 minus, K4 subdivision, one subdivision. You can go back and check. And this will imply that, and our graph, this will imply that there's a lower bound of, okay, before mentioning this lower bound, one can actually prove that for this function, it's known the Zarankiewicz number for one subdivision of K4 is big O of m to the 3/5 n 4/5 for any m bigger than m at least 2. And in our case, we have this is size m, which is QQ plus 1. This is size n, which is Q squared minus Q plus 1, if you recall. And the number of edges here, E, in this incidence graph, G, is Q plus 1 regular for all the vertices on the n side, which is Q to the 5 plus little o, lower order term. And this is precisely m to the 3/5, n to the 4/5, matching this upper bound for this particular choice of m and n. So it will be interesting to find other choice of m and n where we can meet this lower bound. So in general, for one subdivision, there's a conjecture by Conlon, Lee, Genzer and Lee, that if you look at one subdivision of the symmetric case, one subdivision of Ks, then this, what they conjecture is big theta of n to the 3/2 minus 1/4 s minus 6. Here they prove already the upper bound, so we need to find a lower bound construction. This even for K4 is open because for K4 we only have the asymmetric case. But I think for Ks, if we have an asymmetric version when m is polynomial in n, still it will be very useful for deriving off-diagonal Ramsey number. So a consequence of this, why this is important, a consequence of this is that you can use random block construction. The idea here, use the random block construction. And use such a lower bound construction for one subdivision of KS3 thing to prove that RST, the other off diagonal, is up to polylog factor t to the s minus 1 as t goes to infinity. Okay, so for s equal to 5, that will be the next open case for the off diagonal. This is the remark I want to make. Any question? All right, so I want to mention another conjecture also about existence of biregular graphs with large girth and additionally dense. So one can again use this random block construction to get Ramsey number for clique versus cycles. And to do this, the original graph that we start with, we will require some high girth graph. Okay. To state this, let's define some biregular graph. So definition. So we say a graph and M N A B, let's say M is less than N. I think A is at most B. An MNAB graph is what? It's nothing but it's a bipartite graph with M vertices on one side, M vertices on the other side, and every vertex here is A regular, and every vertex here is B regular. That's it. Biregular is an MM vertex bipartite graph, which is biregular with degree A and B on the sides of N and M respectively. Very simple. Now, let's look at what? Let's look at the neighborhood clique graph. Okay. Now what we want to do is look at here. If we do the random block by construction on the M vertex side, what do we do? That means for every vertex on the M vertex side, we're gonna in its neighborhood plant a random bipartite graph. Right? We're gonna add this. Now if we but what we would like is we don't want cases like this. You have another vertex whose neighborhood is almost the same, right? Originally this is a clique. We want this clique to be edge disjoint. They share exactly one vertex or at most one vertex, which translate here is that this graph, bipartite graph, is C4 free. So consider a C4 free MNAB graph. Now do the random bipartite block construction on the M vertex side as above. Okay. Then we will get, let's call this graph H. We get the graph H star, let's say. We again have, for this H star, has some pseudo-randomness property. So before, we have it for this side is the, recall, before, in this K4 construction, this side is the points in the unital U. And the other side are all those secant lines here on the other side. Okay. So here's a lemma which is useful. I will not prove it, and it says that for every C4 free MNAB graph H, now you do this random bipartite block construction on the M vertex side, you get H star. Then conclusion is with high probability, we have pseudo-randomness property that for every vertex set X, at least size R, where R is some constant times M log N over A. Okay, then the number of edges inside this random block construction induced by X is at least A squared over some constant times M times X squared. Okay. Let's compare with before. Before we have M is roughly QQ. N is roughly M is what? Q cube, yeah. N is roughly Q to the 4. Well, actually, let's be precise. Q plus 1, Q squared minus Q plus 1, Q plus 1, Q squared. This is for U and S, right? And what is this guy? This guy will be M over A, which is Q cube over Q. So it's roughly Q squared log Q. Here is what? A squared over M is roughly 1 over Q. So it's X squared over Q. So if we use this lemma, we get the optimal density for subsets of size at least Q squared log Q. This lemma is slightly weaker because in the original K4 proof, we don't have this log factor, okay? So I will leave as an exercise for you to compare this one and the original proof and see where this is more general because this is for all choice of M and AB without any structure on. Before we have some structure information from these unitos and seconds, right? Here there's no information. We just know that it's a biregular graph, but still we have such pseudo-randomness property. So exercise to check both proof and compare, see where we gain this log factor. Compare this with the original, with the K4 construction to see how we gain a log factor there. Okay. So here's a conjecture by Holland, Mathis, Mubai, and Verstraete. They conjecture the existence of a dense, high girth biregular graph. There exists an infinite sequence of MN AB graph. This is an M by M vertex biregular graph with degree A and B on each side of girth. Well, I should say for any L to measure the girth, and for any alpha at least 1, there exists an infinite sequence of biregular graph of girth larger than 4L plus 2 with big omega of Mn to the power L plus 1 over 2L plus 1 edges, where you say N. All right, there's a relation between A and B. Basically, we want M and N to be polynomially related. One is a polynomial of another. This is what it means, basically. Log A of B tends to alpha when you have this infinite sequence. So if you have such a dense biregular graph, you can use similar idea here to get, so the consequence of this, the point of this conjecture is that you will imply almost optimal bound for cycle versus click, fixed cycle. This is consequence is Ramsey for fixed cycle. Let's say C, K, C, 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 L. No, but this is different L. Let me use a different one. C, S, K, T, where this is fixed. Okay, this goes to infinity. All right. Here are two probably hard conjectures, but if you can solve some spectral cases, it will be very substantial, I think. Both these two conjectures. Now let's move on to a very related. This is an earlier appearance of random block construction is not the first appearance in this K4 versus K-clique Ramsey. Let's mention another application of such random block construction on so-called Erdős-Roger function, which is an extension, can be viewed, of a Ramsey function. So let's introduce this Erdős-Roger function. Erdős-Roger function. So what is Erdős-Roger function? Definition is, let's just directly give you the definition, and then we're going to explain. For integers r and s, where r is a smaller one, r is at least 2, we define the Erdős-Roger function f rs of n to be okay. Maybe let me first define this. For any r at least 2 natural number, let's define in the graph, let's define alpha sub r of g to be the maximum order of the induced subgraph of G, which is KR3. Maximum order of an induced KR3 subgraph of G. Okay. In other words, this is the same as maximum of U, where U is a subset of V of G, right? Such that G induced on U is KR3. So why I use this notation alpha sub R? If you take R to be 2, this is not something that's completely strange. If you consider, for example, R equal to 2, alpha 2 of G is just the independence number, right? Because the order, what is an induced K2 free subgraph of G? It's just an independence set. So alpha 2 of G is independence number. Alpha 3 of G is the largest subgraph, induced subgraph, which is triangle free, so on and so forth. Now we can define Erdős-Roger function. FRS of n is the, what you want to do is you want to take the minimum of alpha R of G, where G is n vertex KS free. Okay, that's it. Let's make a connection of this function with the Ramsey function. I claim that this is basically if you take r equal to 2, it's the inverse function of Ramsey. So, remark. If you consider r equal to 2, then f2s of n is the inverse function of Ramsey. So it's basically the same as Ramsey function. So it's more general because now we don't have to take R to be 2, we can take any R. Why is this true? If R equals to 2, we are looking for, this is just normal independence number, right? In the graph, which is KS3, this is basically the largest independence set we can always guarantee in the m vertex KS3 graph. That's precisely the inverse function of Ramsey, right? Is that clear? Okay. If it's not clear, you can try to digest it afterwards. It's basically the same. Now, let's write some examples. For example, we know that R3T equals to n, let's say, where n is roughly up to constant factor t squared over log t. That we know, right? So this is the same as f23 of n equals to t. These two statements are the same. Yeah. Every n vertex graph, if it's triangle free, it must contain, every n vertex triangle free graph contains an independent set of size t. Here, every n vertex triangle free graph must have alpha of g is at least this minimum one, which means it has an independent set of size t. It's the same. Equals to roughly square root n log n. So here's example. And now we also know F24 because of the Ramsey results. So Ramsey R for t is roughly t cubed up to polylog. This implies F24 n is up to polylog what? N to the 1/3, right? Good. So today we're gonna see an example of Erdős-Röjter function where R is not 2. Let's look at the first simple case when R is not 2. It's F34. This is the simplest case, which is not Ramsey. It's more general than Ramsey, but the simplest case. Consider, now we're gonna consider F34 of n. So what is F34 of n? Basically, it's asking how, let's write it down by the definition, how large a triangle-free induced subgraph can we guarantee in any m vertex K4 free graph. This is what this function is measuring. Okay. Now, by these Ramsey results, well, F34 is at least F24. Because if you can find independent set, the independent set definitely is also triangle free. It's easy to get the lower bound. Let's get the lower bound. Observation. Easy to see. By Ramsey number R4T is at most T cubed up to some constant. We get, so it's inverse function. The upper bound on the Ramsey, you get lower bound on the Erdős-Röjter. You get F34 of n is at least n to the 1/3 by just finding an independent set of size n to the 1/3 in an m vertex K4 free graph, right? What does this mean? Once again, every m vertex K4 free graph has an independent set of size n to the 1/3. And this independent set definitely is also triangle free. So we get n to the 1/3 as lower bound. This bound, can we improve it? The answer is yes. There's a simple way to improve it. Let's improve it to n to the roughly square root n. Okay. So now let's prove that. Let's easy. Let's say proposition F34 of n is bigger than square root n. Maybe over 2 or something. Okay. Maybe we don't even need this over 2. We can get 1 plus little 1 or something. Check the calculation more carefully. The proof is simple. Proof, first case. Let's say, do you have a vertex of degree at least square root n? If there exists a vertex V with degree square root n, the key observation here is that the graph is what? K4 free. So the neighborhood of a vertex is triangle free. So this MV is triangle free. And that's it. This is the, if you look at this induced subgraph, it's triangle free. So alpha 3, what this means is that alpha 3 of G is at least maximum degree of G, right? If you have a vertex degree at least square root n, by taking its neighborhood, I should say K4 free. G K4 free implies MV is triangle free, which implies this at least square root n. Then we are done. Happy. Now, if this is less than square root n, just by greedy algorithm, the independence number, we can even find the independent set of size, this, right? You pick a vertex, throw its neighbors away, pick a vertex, throw its neighbors away. So this is at least square root n over 2. Okay, also done. If we look at this proof, it looks like, so our goal is to what? To find the large triangle-free subgraph induced. In the first case, we did find the induced triangle-free subgraph. But in the second case, we actually find an independent set, which seems stronger than what we need. So that might seem a little bit wasteful. So in the second case, we found an independent set, which seems wasteful. We just need triangle free. So natural question is, can we get larger than square root n for this F34 function? Is it possible to be larger than square root n? As it turns out, square root n, even though it's a little bit wasteful here in this argument, this simple argument already determines the order of magnitude of at least the power of n for F3n. So this is a result by Wolfowitz, who proved that F3n is at most square root n times some polylog n. This is the construction we want to see. So but it turns out that square root n is almost optimal. Is optimal up to polylog. It's a theorem. Both of it prove that f3, 4 of n is m most square root n times some polylog factor. Polylog factor doesn't important. It's not important. So let me just put some constant on the power. Let's first say the idea. The idea is the idea is simple. Idea. It's also random block construction. So what do we do? Here, let's first say our goal, right? Let's be clear what we need to do. The upper bound, it's the inverse of Ramsey. Ramsey upper bound, you need to prove an argument. Lower bound is construction. So here, upper bound for Erdős-Roger is a construction. This is at most that. Translate this upper bound by using definition of Erdős-Roger function. It means that if we let go, if you set t to be roughly, if you set s to be roughly square root n, I think we set it to be square root n like log n to some power. So roughly square root n, let's say 110. We need to show that there exists an n vertex graph, which is K4 free G, such that alpha 3 of G is smaller than S. This is what we need to prove. Okay. You don't have upper bound means there exists a graph K4 free, which does not have a large triangle free induced subgraph. So i.e. alpha 3 of G is less than S. Okay, the idea. The idea is we're going to start with, again, some structured graph, which will be the point line incidence graph of projective plane again. We start with so that means we have points and line. Let's say you have q squared plus q plus 1, q squared plus q plus 1 on each side. Point line incidence graph means it's adjacent when a point P and L are adjacent when P lies on L. We first do a sparsening on the line side. So let's zoom into a subset of let's first zoom into a subset of L prime lines. So sample, start with this, and sample with probability. What's the probability? Roughly 1 over q up to polylog factor. So before this, about q square lines, let's zoom into roughly q polylog q. So the probability, I believe, is log Q square over Q. Yes. Okay. Sample with probability lines from L. So what you get is you get the subset L prime in L, a random subset of lines. Now, what we do is we do the random block construction. And the random block construction is very simple. For every line L in L prime, we look at its neighborhood in P. Once again, recall that this is projective plane. So the incidence graph is C4 free. In other words, if you take different lines and look at their neighborhood, this neighborhood, they share exactly one vertex, right? I forgot to say. In point line incidence graph of an order Q, a projective plane. Now we sample a subset of lines with probability log Q square over Q. Now, this is the first step. Second step, for every point, for every line in L prime, plant a random, now not bipartite graph. You plant a random tripartite graph. Complete tripartite graph. Complete tripartite graph. In the neighborhood of L, in this incidence graph. So in the picture, it looks like this. You arbitrarily partition. This just means for every vertex in the neighborhood here, you assign value 1, 2, 3 with equal probability, right? You partition roughly the vertex into roughly same size 3 parts. Now you draw the complete tripartite graph over these 3 parts. Why now we do complete bipartite, complete tripartite instead of complete bipartite? Because our goal is what? Before, we want independence number to be small in Ramsey. To have independence number small, for every small set, we want to see some edges there. So bipartite graph will do the job. But now we want the alpha 3 independence number to be small. What it means is that over some small set, we would like to see some triangle. So if you plan bipartite graph, is useless. There's no triangle. If you plan complete tripartite graph, there's lots of triangle. And hopefully later, if we need to modify the graph, this triangle will survive when you take a not so small set. You will prove that the alpha 3 independence number is small. So this is the random tripartite block construction. And after doing this, we can show that this will imply that with positive probability, we have the following property. For every, now we just look at this, we get this graph, let's call it H, let's again call it H star maybe. So with high probability, H star satisfies this property. For every edge in H star is in a small number of K4. Small means polylog n. Okay, small number of K4. eventually we will want K4 free for this graph to be K4 free. We're going to do some deletion process. And the second property is that for every we want to prove alpha 3 of G to be less than S. So here we can have for every S set, a set of S vertices, it has many triangles. Many triangles. And many means at least S times some polylog S. Polylog N triangles. And furthermore, these triangles are almost edge disjoint. Almost edge disjoint. What does that mean? That means each triangle in this S set shares an edge with at most a small number of other triangles. Here, this small is again polylog N. If we have this property, the final step is to bootstrap this property. Bootstrap that every edge in small number of K4, and we delete some edges to make the graph completely K4 free. And second one, we know that every S set has many triangles, and hopefully, because of this edge disjointness, when we delete this K4 by deleting some small number of edges, we don't destroy all the triangles inside every S set. So at least one such triangle survive, which will prove that alpha 3 of G is less than S. This is basically a variation of so-called K4 free process. So now we do a K4 free process. Starting from H star, we're gonna order take a uniform random ordering of edges of H star. Okay, so every edge of H star, you give an ordering number 1, 2, 3, 4. Let's say this is 5. Give an ordering. So the edges come in order. Now what we do is along the order E1, E2, let's say E1, E2, we want to take a random subgraph of E star. How do we take the random subgraph? So we're gonna get a random subgraph. Let's call it H in H star. How do we get it? You go along this random sequence of edges, E1, E2, E3. You throw it into H as long as it does not create a K4. That's it. So what's the bad case? So put EI in H as long as it does not create a copy of K4. What this means just that this is the bad case, right? In this case, all the other 5 edges of a copy of K4 comes in this order before E, the order of E. Then when it comes to picking E, all the previous ones have been chosen already. If they have been chosen to be in H, then we cannot pick E. We just discard it. Okay? You discard E if some K4. In other words, you discard E if some K4 containing E has all other 5 edges come before E, and they all get picked. They all get picked for H. This is just what it means. Simple thing. Then one can check that doing this K4 free process, first of all, even though this is a random graph with probability 1, this is the property of this K4 free process. We don't keep any K4, right? Every time if some edge going to create a K4, we don't put it in H. So definitely the resulting graph is K4 free. But then we can also prove that with positive probability, there exists an outcome of H such that for every S sets, one of these many triangles, one of these many almost edge-destroying triangles will survive in H to prove that alpha 3 of H is less than S. Okay. Any question about the sketch of the proof before I mention some details? Maybe let me mention the very last step, this K4 free process. How we're going to use this property to carry out this K4 free process. If I have time, I will prove some part of this, how this property can be, how this property can hold with positive probability in H star. If there's no time, I will leave for you to fill in this detail. And so let's assume this and try to carry out the K4 free process. Let's write down precisely what these two property means. Once again, this two property means after doing this random block tripartite construction by taking some small subset of random lines, then the resulting graph has the following two property. Every edge is in few number of K4, and every S set, roughly square root n size, has many, at least linear in the set S, many almost edge-destroying triangles. This is this lemma. With positive probability, H star satisfies the following property. Every edge is in at most 32 log n to some power copies of K4. Second property, every set, every S set of vertices is nice. So what does it mean nice? It just means that it spans regular, a lot of edge disjoint. So this means S of the vertex sets is nice if S spans a family TS of triangles of at least s log n to some power, so at least s triangles, such that they are almost edge disjoint, such that every triangle shares an edge with at most other triangles in TS. Okay. In other words, in short, S spans a family of linear in S, meaning almost edge disjoint triangles. Given this lemma, how do we, so we have this graph, assume that we have this graph. How do we do this K4 free process to get our final graph, which is m vertex? And recall S equals to, recall S is square root n log n to some power. We need to prove that we can use K4 free process to kill all this K4, and every S set, at least one triangle in TS survive. Okay. Let's first prove right. So this is what we need to prove. After the K4 free process, this is the lemma. We know it's K4 free already. We just need to prove alpha 3 of G is at least is at most S. So with positive probability, for every S set, there exists a triangle in TS such that, let's call it T, there exists a triangle T in TS such that T is also in H. So remember, we have H star, you get H through this K4 free process. Okay. If we can prove this, we are done. This will imply that with positive probability, this random subgraph satisfy alpha 3 of G is less than S, right? The following, this is equivalent, i.e. Alpha 3 of H is less than S, and H is K4 free. Then we are done. We're going to use union bound to prove that with positive probability for every S set this holds. That just proves that for a fixed X set, this holds with very high probability. So by union bound, suffices to prove that with fixed set S for a fixed S set S in H, the probability that there exists a triangle the probability that there exists T in Ts such that T is in H is at least 1 minus n to the negative 2s. This is enough, right? Because this bad event, the failing probability is n to the negative 2s, and the number of choice of s sets is at most n to the s. Summing up all this failing probability for all n to the s instance of s sets, the total probability is still bigger than 0. Then we are fine. To bound this probability, let's first bound an event. Let's call it for a triangle ET in this collection of triangles. Let's define the event ET, which is the event that define the event. We define the event is, we need some notation maybe. Okay, wait a second. Define for a triangle, let's define A sub t to be the union of all k minus t over all k. So what is this k? Where the union is over all copies k of k4 in H star. Okay, in H star, where it shares at least an edge with the triangle T. Let me draw some picture. Here is T. Okay. What is AT? This is a K. This is a K, right? That's a copy of K4 sharing an edge with T. No. If share a vertex, we don't care. Because all we cared about deleting edges. We don't care about vertices, okay? We don't care such K4. So another example, for example, it could also look like this. K prime. This is also possible. It could intersect with share at all three edges with T. That's also possible. Good. So this AT is all these copies with edges in T removed. Okay, so it's these blue and green edges. This is AT. Why we define this AT? Because a triangle T survive in this K4 free process, survive in H, if and only if you look at these three edges, remember, we order the edges of H star in a uniform random order. When does this T survive in H? If the order of these three edges come in the first three among all such edges. If comes at the very beginning, then all the K4 involving these three edges come later. Of course, when these three edges were considered at that moment, no K4 can be created using these three edges, right? So that's why we consider this set AT. We can now define this event. Define the event. define event ET, which is the event that all edges in T comes in this random order comes all before all edges in AT in this random ordering. Okay, this is the event. So what do we know about this event? By the K4 free process definition, this event will imply that T will survive in H, right? This is what I just said. ET. Okay. So let's estimate the probability that for a single triangle T, this good event, that T survive in H. That's a good thing, right? We want, once again, where are we now? We fix a set S. We want to estimate the failing probability that no triangle survive is small, or there exists at least a good triangle that survive has high probability. So for a fixed triangle, it survive as long as this event holds. What's the probability of this event? The probability that ET holds for any T this is what? This is simple. We want these three edges in T comes first, right? E1, E2, E3. And then all the other edges in AT. So the total permutation, all the other orderings doesn't matter of the other edges. So the total ordering is size of AT plus three edges in T factorial. This is total number of ordering. And the good ordering we want, so that T comes first, you can order vertex edges in T randomly, 3 factorial. After you order that, now you order the remaining AT, which is AT factorial. These are the good ordering where T comes first, right? This, if you do the calculation, let's first upper bound size of AT. The note that, note that AT is not so big. It's at most, how many edges in AT? Once again, AT is those relevant K4 edges that share an edge with T. Well, first of all, there are 3 edges in T. So it's at most 3 edges in T. And then for every such edge, remember our property. Every edge is in at most polylog, meaning K4, times is in at most 32 log n to the power 8, meaning K4, right? Every edge in at most this many K4. And every K4 have 5 other edges. At most 5 other edges. Some of these K4, the new edges only 3, right? But 5 is the most. So this is at most log n to the 9. Very few. So using this, we can lower bound this probability, which is at least oops, log n to the negative 30, say. So quite decent, not too small. Now, let x, so now let's define x to be the number of triangles in TS such that this ET holds. ET holds means T survive in the final age. Linearity of expectation implies expectation of x is equals to sum of T in TS, the probability that ET holds, which is at least number of triangles in TS times this probability. Okay. Now we're going to use what we want to show is EX. We need to show, this is what we need to show. Recall what we need to show. The probability bad events is X equal to 0, right? This is bad event. Bad event means for this fixed size S, fixed set S, the number of T where it survive is 0. No triangle survive. So as long as we can upper bound this probability, we are done. So we need to upper bound this probability by at most n to the negative 2s, which then will imply our good probability will imply that this will imply alpha 3 of h big smaller than s. Okay, I don't want to write this. Right? It should be clear. Good. Oh, there's a question in the chat. So this random block construction, you can plant random tripartite, random four-partite, random five-partite. Depends on probably this FRS, the value of R and S. You need to look, you need to check what property you need. So we are left to bound this probability that X equals to 0. Basically, we have a lower bound on the expectation of X. All we need to show is now we have a bunch of events, ET, because ET is almost edge disjoint. So we want to say that this ET, they are not so dependent on each other. So you can use, for example, boundary difference inequality, McDermott inequality, the concentration inequality to bound to show that the probability that X, this random variable, is around its expectation with very high probability. So this is the event that X is not around its expectation, right? Its expectation is very high. This is like S polylog n. This is polylog n. Cancel out. S is roughly square root n. So this deviates a lot from the so we just need to prove this X equal to 0 is at most the probability that X minus EX, the deviation, is more than half of the expectation, right? Expectation is way much larger than 0. So, and this you can bound by n to the negative 2s using, for example, McDermott inequality. Bounded difference inequality, some concentration inequality. So for this, you need to show that do I have time to talk about this? I don't think I have time. This is some standard detail. Basically, what you want to check is that using here, this part, we use the fact that TS is almost edge disjoint. Okay. Let me briefly mention the idea. The random thing is the edges. It can't mean some random order. So what we want to show is that if you change if an edge, how much difference an edge can make. So you have to look at how many triangles and K-folds this edge is involved in, which is a small number. So changing an order of an edge can only affect this value of x by a small amount. Basically saying that they are almost independent in some sense. If it's almost completely independent, you can use Chernoff. So this is a strengthening of Chernoff's, sort of saying that if the dependence is not so strong, you can still get very, very high decaying probability. All right. Any question? I will leave for you to fill in this detail. Okay, fill in detail. This is just technical details. I think more important thing is to understand these slides. If your goal is to find the n-vertex K4 free graph with small alpha 3 independence number, the idea is you start with projective plane, then you do a random sparsening, complete tripartite random block construction, which will give you all this nice property. Field C4, field K4, every edge in field K4, and every square root n size set will have many triangles, which is good for proving alpha 3 of G is small. And these triangles are almost edge disjoint, so later it's good for using concentration inequality. You can use K4 free process, meaning you randomly, uniformly order the edges of this random block construction graph, E1, E2, E3, E4. You just go through this order, put this edge into our final random graph H. As long as this current edge EI does not form a K4, with some previous 5 edges that's already picked to put in H. Okay. Any question? So I skip some details. Here, that's one part. The details to fit in. Another thing is to prove this lemma. Fill in the detail. There's also some exercise for using some concentration inequality. So someone asked if there's a workshop, if winter school. Yes, there is a winter school. We're gonna announce it soon. Probably in the first half of January, we will have a winter school taught by Hui Fan from Stanford on this threshold phenomenon. Again, similar to the summer school, this will be a 5-day lecture. Each lecture 1.5 hours on this Conca-like conjecture and related things. Right? Other questions? Okay, if there's no question, we're gonna move on to a different type of geometric construction on Thursday. See you guys then.